All right, so those sample exams are on Moodle. I didn't really look at all of them. I looked at a few of them, and so I don't know how much they have in common. I am going to try to write your exam fresh and not really look at those old exams. So while I'm sure some questions will be somewhat similar, there could be some differences as well. I did happen to notice, like I mentioned, that there was a topic on those old exams that we have not covered in class here, and in fact, it evidently was in an older edition of the book, but it's not in this edition. It's something called the Euclidean Algorithm. So I think it's worth talking about here at the beginning today, so we'll talk about that. It's basic number theory. It's nothing super difficult. And that really is an algorithm, by the way, unlike the division algorithm. And we'll talk more about subgroup lattices in relation to cyclic groups and get into a lot more depth about permutation groups in both lectures A and B, hopefully. All right, so what is the Euclidean algorithm? It's one more bit of number theory worth knowing. The main idea is that you repeatedly use the division algorithm to find the GCD of two numbers. From that, you can also use something called back substitution to express the GCD as a linear combination. Okay, so we've used the GCD as a linear combination theorem as a more theoretical tool for proofs, but here you can actually use this technique to actually find the linear combination. Let's do an example. This example is with some kind of big numbers, but let's go ahead and see it in action. I brought my calculator with me here so I can help avoid mistakes, which I think I do need today since I had such a difficult morning. Let's see here. How do we do this? The algorithm says when you're trying to find the GCD of these two numbers, first take the bigger number, 9,900, and divide it by the smaller number, so you get a quotient and a remainder. So 4158 is going to go into 9,900 twice. So we can write 4158 times 2, but then there's going to be a certain remainder. Okay, I can do this in my head, but hopefully avoiding mistakes, I will use my calculator. The remainder is going to be 1,584. Okay, right? Just do 4158 times 2 and subtract it from 9,900 to find the remainder. Then you repeat this process. Make the original, I'm forgetting the word, is a divisor or dividend, the one that goes in the bottom of the fraction. I think it's, I forget the terminology. Take that, 4158, the thing you were dividing by originally, and make it the thing that you are dividing into now. Take the original remainder, and we are going to take 4158 and divide that by that previous remainder. 1584 is going to go into 4158 twice. And what will be the remainder? It will be 990, which it's just a coincidence that that is 10 times smaller than 9,900. Okay, that's just a coincidence. Repeat. Oh, we meant to draw an arrow there too. Take 1584, divide by 990. 990 is going to go into it once. I think I can do this in my head. Plus 594 is going to be the remainder. Take that 990, divide it by 594. 594 is going to go into it once, and the remainder will be 396. Yes. Keep going. When do we stop? When does this algorithm stop? It stops when we get a remainder of 0, actually. 396 goes into 594 once with a remainder of 198. And it is going to be in this next step that we get a remainder of 0. $396 is going to be 198 times 2 with a remainder of 0. So we stop. So what's the GCD? The GCD is the last non-zero remainder. That right there is the GCD of 9,900 and 4,158. Maybe, I'm pretty sure that's right, but maybe we should double check in Mathematica. Mathematica's got a built-in GCD command. GCD 9900 and 4158 is 198. Okay? So Euclid was, again, somebody who lived a couple thousand years ago, came up with this algorithm for finding the GCD. It's called the Euclidean Algorithm. Do you have to program this in Computer Science 1? Sometimes they've given that assignment where you have to actually program the Euclidean algorithm. Okay, evidently not for you guys. All right, but now we can also use it, use all these equations, and back substitute to figure out how to take 198 and write it as a linear combination. Better make sure I don't make a mistake here either. Let's do it down here. So take the 198. Use the second to last equation here. Solve for 198. Write it as 594 minus 396. Then back substitute, in other words, go to the previous equation, solve it for 396 and substitute. And be careful about not making a mistake. Solve that for 396, it's 990 minus 594. Probably worth simplifying that in terms of 594 and 990, a linear combination of those two first. That's going to be the same as 594 times 2 minus 990. Back substitute, go back to the preceding equation, solve for 594 in terms of 990 and 1584. 594, looking at that equation, is 1584 minus 990. That gets multiplied by 2 and we subtract 990. This is going to be 1584 times 2. And then combine the 990s and the 2, you're going to get what? Just a minus, let's see, minus 3 990? Minus 990 times 3. Check that I don't make a mistake. That looks good. Couple more steps. Go to the previous equation again, back substitute. We're going back and we're substituting. Solve that for 990. So we have 1584 times 2 minus 9. What's 990? 990 is 4158 minus 1584 times 2. And don't forget to multiply that by 3. As a linear combination of 1584 and 4158, this will be what? 1584 times 5. 2 minuses make a plus. And then minus 4158 times 3, or if you prefer, plus 4158 times negative 3. Now replace 1584 with, did I make a mistake?
1584 times 2 times 3.
Thank you. So we have really a 6 and a 2. We got an 8 there then. Look good? 1584 is 990 minus 4158 times 2. We're almost done. 9,900 I meant to say. Minus 4158 times 2. That gets multiplied by 8. So it looks like we have 9,900 times 8, and then what? Let's write it as a plus. Plus 4158 times a negative number. That negative number would be what? Negative 16, negative 19? Is that right? Look good? All right, let's double check that. Oh, I could just use your calculator. Do subtraction. Okay, I guess I can do it all at once. 9,900 times 8. I'll do it as minus 4158 times 19. Does come out to be 198. So imagine trying to find S and T without doing this. Yeah, this is probably the best way to find S and T, to write the GCD as a linear combination. By the way, the S and the T are not unique necessarily, but this is one solution. Okay, it's worth knowing. You'll see it's on some old exams. Will I test you on it? I don't know. I've only shown you once. If I do test you on it, probably it would be with smaller numbers. Okay? It is worth knowing. If for nothing else, then say 50 years from now, you're at a cocktail party and with a bunch of mathematicians, and they say, oh, what major were you in college? And then you say, oh, I was a math major. And they say, oh, Euclidean algorithm, wasn't that great? And you're like, what? Euclidean algorithm? I never learned that. Well, you have. Not that you'll remember it, but now you have, okay? Just in case, you never know. All right, so then we hinted at the idea, we talked about the idea of a subgroup lattice last time. Let's review that idea. We can even review it in the context of S4, this new group that we talked about at the end of lecture B last time. S4, the symmetric group on 4 objects. What is that? You think you could say what it is? Maybe I should make this kind of thing a quiz question. As a set of elements, what are the elements? They are they numbers? Are they matrices? Or something else?
A permutation, where it goes from 1 to 4.
They're permutations, which means, in this class, it means they're functions. Called the set of all alpha, such that alpha is a function mapping. We can take it to be the set 1, 2, 3, 4 to itself. That's 1 to 1 and on to. There's my shorthand notation for 1 to 1. It's not an H, 1-1. They're functions from this set to itself. Why are they called permutations? It's because they are essentially reordering the numbers in there. As you've learned about permutations in the past, you can think of permutations of objects as putting them in a certain order. And that's what this does. Essentially, you know, if alpha of 1 is 3, alpha of 2 is 1, alpha of 3 is 4, and alpha of 4 is 2, then you have, in a sense, reordered the numbers in the order 3, 1, 4, 2. That's what alpha has done in that case. And the operation is function distribution. And then from chapter 0, it's important that when you compose 2 1-to-1 functions, you get a 1-to-1 function. When you compose 2 onto functions, you get an onto function. And such functions have inverses. And the identity element, it's called epsilon. You remember from me reading what that is? What's the identity element? It's a function that does what?
Not the same number to its name.
Yeah, maps every number to itself. You could write a formula for the identity function, epsilon of x equals x for all x in the set 1, 2, 3, 4. The identity function maps everything to itself. That is the identity. S4's got lots of subgroups. I got this off online. I didn't double check that it's definitely correct. I'm assuming it's correct, but evidently the dots are representing elements. Okay, though it's not clear what elements they represent. probably the black dot is the identity, though, since there's just one of those in each of these, including in the trivial one down here. As you go upward, you're getting bigger and bigger. As you go downward, you're like talking about subgroups. This is a subgroup of that, this is a subgroup of that, this is a subgroup of that, etc. This is a subgroup of this and that. How many elements does S4 have? What's its order? This is related to discrete math too.
4 factorial.
4 factorial, right. 24 elements. Because for the first output, you've got 4 choices. For the second output, since this function's got to be 1-to-1, you have 3 choices left. For the third output, again, since the function has to be 1-to-1, you've got 2 choices left. And that means the last choice is fixed. We've got 1 choice for that one. 4 times 3 times 2 times 1. 24, 4 factorial possible outcomes. In general, the order of Sn is n factorial. We have 24 elements up here. Yeah, I think if you count at 24, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 dots there representing elements. Again, the black dot represents the identity. Evidently, I'm not sure yet what the other ones represent. I could probably figure it out. I just haven't taken the time to do so. It's got subgroups. Evidently, some subgroup like that that's got 2 elements would be the identity in some element whose order would have to be. If a group has 2 elements, what would the order have to be of the non-identity element? 2, right? Raise it to the second power, you got to get the identity. It's groups of order 2 have to be cyclic. Interesting, there's a theorem. Any group of order 2 has to be cyclic. Any group of order 3 actually also has to be cyclic. I guess that's a group of order 3. The identity and evidently 2 elements of order 3. They can't both square to give you the identity. I'll let you think about why that can't be the case. This is the most famous quote-unquote subgroup of that. A4, it's got exactly half the number of elements. 12 of them. Turns out these permutations are called even permutations, and if you've done your reading, you know what that is already. If you've done reading, but we'll come back to this. So you can make subgroup lattices for any group. And what I hinted at last time should be true. If 2 groups have 2 different subgroup lattices, they don't have the same structure as graphs, say, with vertices and edges. They don't have the same graph structure. In fact, it's really a directed graph. Then the 2 groups cannot be isomorphic. They cannot have the same form. Doesn't mean if they do have the same subgroup structure that they are isomorphic. That's not necessarily the case, and in fact, it's not true. But if they have different subgroup lattice structures, then they can't be isomorphic. For cyclic groups, the subgroup lattices are relatively simple, especially if the cyclic group happens to have an order that is a power of a prime. Let's do it for Z this time. Take Z to be, for example, say, Z27. Cyclic group of order 27. 27, what are its divisors? Divisors of 27 would be 1, 3, 9, and 27. By the fundamental theorem for cyclic groups, you've got exactly 1 subgroup of this cyclic group of each of these orders. So the subgroup lattice is pretty simple. You've got the whole group up here, which is generated by 1. Then you've got the group of order 9, generated by what? By the number 3. or A cubed if I was using generic group, cyclic group of order 27. Nine generates the subgroup of order 3. And then there's the trivial subgroup, which you can write with a 0 there, which seems a little funny because the numbers keep going up and up and up, and then they go down to 0. Well, you can think of it like that as well. 27 being the same as 0. But that's not technically the best thing to write for us, since we were, as sets, we were thinking of this as just including 0 through 26. 27 was not really an element of this set for us, but it's, effectively it's that kind of thing. If you were thinking about making the cyclic group with equivalence classes, mod 27 like I talked about a week and a half ago, the equivalence class containing 0 also is the same as the equivalence class containing 27 in arithmetic mod 27. And you could do that kind of thing. I won't mark myself as being wrong here, but ideally, do it that way. So if the cyclic group has an order that is a power of a prime, then the subgroup lattice structure is very simple. You did an example where your cyclic group had order p squared times q for two different primes. In between those two cases would be a case where the order is p times q, the product of two different primes, like Z15. As 3 and 5 as prime divisors. Overall, the divisors of 15 are going to be 1, 3, 5, and 15. Cyclic subgroup of order 5 is generated by the number 3, and the cyclic subgroup of order 3 is generated by the number 5, and neither is a subgroup of the other, so you should structure it more this way. Not a vertical kind of structure, not a linear structure, but a branched tree. Okay, so that's the second simplest kind of structure in general when you're talking about the order of a group being in terms of a certain product of primes. Of course, when the order is a prime itself, that's a power of a prime. That's really simple. Z7 has a very simple structure, just two things, two subgroups, because the order is a prime. The cyclic group has prime order. It only has two subgroups, the trivial subgroup and the whole group, the non-proper subgroup. Okay, so it's a tool to help us understand groups. We'll continue making them from time to time. All right, now we get on to permutations and permutation groups, our main subject for the day. When I was first introduced to this topic, I thought it was kind of difficult. And I didn't really like permutations of groups at first, but I told you last time, I like them more and more over time. I think they're really kind of fun. They are more complicated than cyclic groups, but that's part of the fun, actually, is a little extra complication. First of all, again, a permutation of a non-empty set is a function from that set to itself that is one-to-one and onto. I'll remind you that one-to-one also is termed injective, and onto is also called surjective, and when a function is both one-to-one and onto, we often say the function is bijective, or is a bijection, just in case you ever hear those words in the future. But we'll usually use one-to-one and onto. A doesn't have to be a finite set. A could be an infinite set. We can talk about permutations of infinite sets, but we're more interested in A being a finite set, and most typically the set 1, 2, 3, etc. through n. A permutation group of a set or on a set is just a set of permutations on A that forms a group under function composition. It doesn't have to be the symmetric group, Sn, It could be some subgroup of that, for example, that we're talking about when we talk about a permutation group. That's just a very special and important permutation group. That would be the set of all, emphasis on the word all possible permutations on this set. All possible one-to-one and onto functions from this set to itself. Okay, emphasis on the word all. So thinking about the fact that it's a group, what do you need? You need closure, really. And that is important to check. You got two permutations. When you compose them, is it a permutation in the same set? The same collection of permutations that you are thinking about. Associativity follows automatically. Function composition is always associative. You never have to prove that from now on. We didn't talk about it. I think it might have come up in one of the problem. Function composition is always associative. Is the identity permutation in there? Is the permutation that maps everything to itself in there? It needs to be for it to be a permutation group. And for any given function in the permutation group, is the inverse in there as well? The inverse function will exist, for sure, but will it be in the set you're talking about? Will it be in the permutation group? Or the thing you are trying to show is a permutation group? So here's Sn, and let's, okay, here's the general description of it. Again, it's the set of all possible permutations on the set, 1 through n. It's called the symmetric group of degree n. I usually don't use the word degree personally. I usually describe it as it's the group of all permutations on n symbols or n objects. If you say symmetric group, you implicitly mean all possible permutations, denoted by S of n. As I've already mentioned, its order is n factorial. And that follows from the basic counting principle, sometimes called the multiplication rule from combinatorics. Basically, you use that kind of multiplication rule in these problems from junior high where you were like, okay, there are 3 different appetizers you can have, and 6 different main dishes, and 4 different desserts. How many different meals can you have all together? And you multiply the numbers to get the total number of possibilities. That's the multiplication rule. In terms of permutations, again, as we talked about, for a given permutation, you've got n choices for alpha of 1, n minus 1 choices for alpha of 2, n minus 2 choices for alpha of 3, because you want it to be a one-to-one function, etc. You've got 1 choice left at the end, if the function is going to be one-to-one, which is what you want. You want it to be one-to-one so that inverses exist. One-to-one and onto. Here's an example. It's almost quiz time here. Let's just start looking at this example here. S3, symmetric group on 3 objects. Set of all permutations, functions that are one-to-one and onto from the set containing 1, 2, and 3 to itself. It's got 3 factorial, 6 elements. Here they are in array notation. So I briefly talked about this notation last time. You read about it. That particular one right there is the identity. The things that are underneath, the numbers on the top, are the outputs of the function. It takes 1 to 1, 2 to 2, and 3 to 3. That's the identity. This is not an identity. It maps 1 to itself, but it transposes 2 and 3. Maps 2 to 3 and 3 to 2. This one, for example, cycles from 1 to 2, then 2 to 3, then 3 to 1. We've got 6 possibilities here. Those are the 6 permutations in the array notation. Turns out that you'll read about this if you haven't yet. that if you set alpha, say, to be this permutation that cycles from 1 to 2, then 2 to 3, then 3 to 1, and beta this one that transposes 2 and 3, and epsilon to be the identity, it turns out you can write all the elements of this group in this way. You can write them as not linear combinations of alpha and beta, because we're using multiplicative notation, but powers of alpha and beta that get multiplied. And it turns out every one of these permutations can be written in one of those ways, though you do need to check that. Okay, and I think we'll check that after the quiz. Let's take the quiz right now.